Today we are going to read about bipolar junction transistor or BJT. So first of all, the word BJT stands for bipolar junction transistor, where bipolar means here we have two carriers. Bipolar indicates that here we have two carriers. The first one is holes and the second one is electrons, which are responsible for the flow of currents. Okay, now we will know what is the need of this bipolar junction transistor. There is a need because it can act as a switches in digital electronics and amplifiers in analog electronics. We can get the control of the flow of current in our hands by using this transistor. These transistors are very important in today's era where all our gadgets are embedded with these type of transistors, of which BJT is a crucial part. So now we will learn in deep about this. First we need to know that it is a 3-terminal device. That means it consists of first is emitter, second collector, and third one base. Now we will know the types of BJT which we can have. So it can be classified in basically two types. The first one is NPN type and second one is PNP type. So in NPN type we have a combination of two PN junctions, N, P, N. We need to know here that emitter is heavily doped, base is lightly doped, and collector is moderately doped. Now the width of collector is greater than the width of emitter greater than the base. Hence base is the narrowest among these three. Now we will know about the different reasons of operations of this BJT. So there are three reasons in which it can be operated: active region, cutoff region, and saturated region. So in active region, the transistor can be used as an amplifier. That means we can get some signal as input and we will amplify it. We will get something gain like this. And cutoff region and saturation region, in these two regions we can use this as a switches. So now we will know in detail about this. And these three regions of operation basically depends on the type of biasing across its terminal. Okay, so first of all we will read about the active region. So we will have a diagram of this NPN BJT transistor. As we know that the base region is the narrowest and the collector region is the widest among these, so we will draw accordingly. NPN, here it is the emitter terminal. Here we are applying biasing to operate in these regions. So first of all it is this potential, which we can say from emitter to base potential. This is in forward bias, and this collector to base potential is in reverse bias. If you will apply the biasing in this way, we will get amplification. So here we can have voltage at base terminal greater than voltage at emitter terminal, and voltage at collector terminal should be greater than voltage at base terminal. So we can write voltage at collector greater than voltage at base greater than voltage at emitter. So this is the biasing condition for operating this transistor in active region, I for amplification. Now we will move towards the cutoff region. I will not draw the diagram again. We can easily know that emitter to base, this potential which we are going to apply will be in reverse bias, and second, that is base to collector, will be in again reverse bias. So if you will apply in this way, we will get cutoff region in which this transistor could be used as a switches. So here also we must have voltage at emitter should be greater than voltage at base region, and voltage of collector region is greater than base region. So these are the two things here. Okay, now the third one is saturation region. Here also the transition acts as switch. So for saturation region, we have emitter to base as forward bias and collector to base again forward bias. Also we have VB greater than V. We are just writing the short form for using this as an saturation region. Okay, so these are the three regions in which this BJT transistor, either NPN or PNP, can be used according to the requirement. Okay, so now we will know about a different configuration in which these transistors will be used. So first of all, we can have as common base configuration, where base is common to input as well as output side. Second one is common emitter configuration. Third one is common collector configuration. So here we are saying common again and again. Common means it is common to input side as well as output side. So these are the three configurations in which we can set up the biasing. Common base configuration. Here base is common to input and output region. Now we will draw the diagram to illustrate this. So here it is the symbol of bipolar junction transistor. Here it is the base. Here we have emitter. Here this arrow indicates that this is NPN transistor. Here we have RE, resistor across the emitter terminal. Okay, so all of these which we are going to read will be in active mode. Active mode means emitter to base we have forward bias and base to collector we have reverse bias. So in this mode we are going to read this three configuration. So it is common base, and here we have base is common to these two, and we are making the circuit. So this base will be grounded here at this point. This is the collector region, this is the emitter region. Here we have, this is the input side, and here we have this, we can say V in, and this is in forward bias. Here this will be in reverse bias. This potential between base and collector we can say VCB, and this potential between emitter to base we can say that VB, and this input side potential we can say Vin or VEE. It is basically denoted by this. So we will get the input signal from this emitter side, and we will get the output signal or amplified signal from this collector side. Okay, so first we will need to know that there can be two characteristics of this configuration. The first is input characteristics. It is the plot of IE, which is the emitter current, versus VBE, potential between base and emitter. And output characteristics, plot is between IC versus VCB. Now in this circuit we can apply KCL, as we know that I is equal to IB plus IC. Here we can see that from this direction I will be IB plus IC. This is valid for any of these configuration. but this is only for active mode. We need to know this. We also know that collector current is alpha times emitter current plus ICO, or IC is equal to alpha times IE plus ICBO. Here ICBO indicates that this is C common, this is base, and this is open circuit. This O indicates open circuit. Okay, here we can take an assumption that emitter current is very greater than ICBO, and this ICBO is the reverse saturation current, which is due to the minority charge carrier. This is what? This is reverse saturation current due to minority charge carrier. So the above equation can be written as IC is equal to alpha times I. So this is very important. From here we can get the value of alpha, that is collector current divided by emitter current. So this we got, and alpha can be basically defined as common base current gain. That means gain of current when base is common to input as well as output side. And we also need to know the range of alpha, which is between 0.95 to 0.98.